So let's welcome you to the sixth lecture on network security. So the last time we have looked into various elements of firewalls, and one of the core elements that we discussed is how the three basic elements, let's say, in networking security is. I mean, how you can secure your infrastructure. So on the one side, basically, if you have various components in your network, then what you typically do is to introduce at a certain point some kind of firewalls that we looked into last time. So it's basically just a filter, and depending on what kind of information it filters, it's working on the various layers. So regular firewalls take into account the IP address and the ports, and whether it's TCP or UDP. So this is more on the networking layer. There we had a look at how some rules can be created in IP tables, but you can also have them at the application layer, where you basically filter based on application protocol data. So such as to only allow HTTP traffic that retrieves data but doesn't push data, so that you can control what, let's say, associates, so employees upload to the internet. So today we will look into intrusion detection systems. That's more some kind of monitoring element that digs deeper into the data. So you have some kind of magnifying glass, and at various points you are able to basically place that intrusion detection system that observes all traffic passing through. So it's often also combined with the firewall, and that allows you to identify malicious traffic. And the last part will be a virtual private network. So if you have here some kind of local network where all the participants can access the services that are attached to these devices, file servers, printers, whatever, then you can have some external nodes creating some tunnel towards those services and act as if they would be in the network themselves. Okay, so let's see where we would start now. Okay, yeah, last time, so also this is I think the last time we looked into Nmap, which is quite useful to identify open ports, open and some services running and offered, so you can identify what kind of vulnerabilities they are. But today we will look into vulnerability scanners in more general step, and basically the main element is so this is still connected to Nmap and to detecting vulnerabilities, so that you can scan from one point in the network. So basically you can reach out to other hosts based on the IP addresses and send out messages and observe the responses to identify what kind of versions are running, what kind of server versions are running, and where you can bring this information together to identify whether there are some known vulnerabilities for these services. Yeah. So this is of course both from the attacker side interesting, but also from the defender side, to identify what is observable from the outside world, what information is leaked that can be used as a starting point for attacks. Actually, to bridge the gap to FB Pro as one of the companies in hardening, this is typically what hardening companies do. So a hardening company or hardening approach, typically what it does is, if you have various devices here, so you have your various devices and there are various services running. And if remotely somebody sends you some kind of messages and the services respond based on the responses of the services, you can observe what kind of service version is running, maybe also what kind of configuration is running. And typically this is the place where hardening is performed. So what you want to achieve with hardening is to reconfigure the system, or to configure the system in a way that it doesn't expose any, so as less as possible vulnerabilities. So typically what you do is, if you identify, let's say you have some file hosting, file sharing service for Microsoft in an outdated version that had some security flaws, you could, for example, enforce through hardening that this service is deactivated, and it is enforced if you need that service, that it's using some more modern versions which doesn't have that security flaws. Also, one obvious reason, so either to increase the use a more up-to-date version, that's one approach that can be done, or you could deactivate, as it is here seen, the malicious, or not malicious, but the vulnerable service that is not used. Or that's typically the case that if you install Windows, let's say, for convenience reasons, all of the features that a user might want to use are enabled. So you can have Bluetooth enabled, you have printer sharing enabled, you can install new printers, you have support for various protocols that are also considered already unsecure, just for compatibility reasons. And these kind of elements are then deactivated or configured in a way that only secure versions are supported. Yeah, maybe I can even show you. I know it's a little deroute now on system hardening, but it might be quite interesting as it fits the topic now. So here, for example, I did some kind of, that's a typical example that shows if you download this audit, how's it called? Audit tab, yes, audit tab. Audit tab, exactly. So what it does, it checks your system for various security issues, for vulnerabilities that are known, but that are still enabled in Windows due to convenience. Yeah, and then you can basically look it up, and you see, in my case, it's quite a lot of red elements. For example, BitLocker is not activated on all volumes, BitLocker is not running, module logging is still is not enabled, it's not set to enabled. Various security elements in the PowerShell script are not enabled. What else? There are outdated protocols still enabled that should not be used nowadays. There are newer versions. There's even the null cipher that doesn't encrypt the data as an encryption method is enabled. And I mean, this is still some finite set of lists of elements that are checked, 1000 maybe for Windows. There's a public open database where these kind of configuration issues are hosted. And typically what companies do, they take this list, they identify where in the registry, at least in Windows, it needs to be checked, and then they check it and tell you everything is quite red. And there's another kind of second program that they sell where it configures your system to not have these vulnerabilities. So this is the core element of hardening, and it's about detecting configurations that show vulnerabilities. And very similar to that are intrusion detection systems, which do not look at static configuration, but which look at okay, I mean, to make it more, so this would be some kind of okay, so hardening looks at static configurations and what could emerge based on that. An intrusion detection system look at dynamic activities, to say that. So one element where you could look at is network traffic, yeah, and for network traffic there are also known and then public databases that list how malicious traffic looks like. So if once in the past there has been some virus that communicated to some, I don't know, command center, what it should do, so it would be a bot or some kind of part of a botnet, then if previous researchers analyzed that kind of traffic, they saw there's always a specific bit pattern in the traffic. In the second message there's something coming, so you could look for that specific pattern at other positions as well, and if you see that pattern reappearing, that bit combination, then you could raise a flag and say, oh, here's something potentially going on. So basically, based on the observations of previous viruses and attacks, there has been created a database with all of these patterns, all of these bit combinations that are suspicious but characteristic for those specific attacks. And if you apply that either at the host, so basically here you have your Windows and you apply it as some kind of application on Windows for all the traffic that goes out and that comes in, that's then a host-based intrusion detection system, or you could have here some kind of router that dispatches the traffic, and you can also apply it in general at the router so that all of the in and outgoing traffic is somehow monitored. It's important that you capture all of the data, all of the network traffic, so that you can observe all traffic passed through your network. And basically, what can you do? If you detect an attack, typically you can raise an alert, inform somebody, and provide the log details of what you found and what you associated to what kind of attack might be going on. There are also intrusion prevention systems which take influence on whether the packet is forwarded or not. So basically they can keep the packet back or drop it if they are very sure that this is an ongoing attack, so they can directly stop it, in contrast to just report and alert someone. So what does it do? What does a network intrusion detection system do? So it can be as in the firewall stateless, so it's looking at individual packets without history, or it could be stateful to observe also connections in general or sessions, and might also be connecting to other network intrusion detection implementations, so to observe whether there's a general pattern. So for example, if you would have, so this is your server and there you have a router and there's some ongoing traffic, and somebody tries to run a distributed denial of service attack. So there are many requests coming from all different directions towards your server. Each individual request is not specifically an issue because they all look legitimate, but if the quantity of requests surpasses some specific threshold, that might be suspicious. If, for example, your web server experiences, 100 requests per day and you get them now per second, that would be some anomaly. So how does it work? So intrusion detection systems, especially network intrusion detection systems, have a set of rules that are very similar to those that we saw for the firewall. It describes, so basically there's a pattern matching. A moment. Pattern matching based on the whole packet and some reaction. So this is some generic model to describe this. And packets and connections are checked against these rules. We will also have some examples. I also have the list of up-to-date rules that I will show you.
Okay.
Yeah?
What kind of requests are you getting sent to the server? Will it kind of be performed with ICMP?
It's for all traffic, so it's not there are no. So one moment. So in this case, if our network intrusion detection system is here, it doesn't send its own. Do you mean what messages it this sends, or what messages it's?
Or do you also have like a specific kind of request that?
Oh, that's. The list is very huge of what is checked for. Yeah, we will come to that in 7 slides or so. So how those rules look like, but it's not limited to any specific protocols. Actually, some of the patterns are also just looking for specific bit patterns in the message itself.
But usually when an attacker wants to perform a DDoS attack, is it relevant, or is it
It's in the case of this denial of service attacks, of course, that should be somehow compatible. It doesn't even have to. It doesn't even have to be compatible to the application specifically. So let's say you run a web server, and the web server is listening to a socket, and every new TCP connection is stored and for later processing. So every TCP connection that is established to the web server is managed by the web server, so that it has its own state, that you know who is communicating with this TCP connection, and that you can associate previous requests, let's say. So, and if there would be just simple TCP SYN requests in a high magnitude, then the web server might open up this kind of memory and state for that newly to established connection. But if the TCP handshake is not completed, then just the resources were consumed and there were no HTTP requests at all sent. So it doesn't have to be really application specific. It can be just very low level connection establishment. So it's really diverse. We will have a look at those kind of patterns. Sometimes this is also the case how signatures in antivirus software works. So where you also typically the antivirus software providers basically regularly send out an update with new patterns, with new signatures. And what antivirus software sometimes does is just to look at the exe files, look at the bytecode it generates, and if it observes specific activities that are characteristics, so not activities, but basically command patterns in this bytecode that are characteristic for specific viruses, then they raise a flag and tell, here's a potential match to a pattern that has been associated with a virus. So very similar, just that in this case it's not exe files that are matched and looked at, but every individual packet. So what can you do? One of the essential elements is logging. A higher reaction, more drastical, is to trigger an alarm. And for the prevention system, it also initiate countermeasures by blocking that traffic and advising firewalls to not accept messages from that source, for example. Okay, so how is that typically set up? So you have quite a lot of sensors. So it's not even too complex. You have network sensors. So basically, if this is the machine, you have a host sensor, some sensors running at the machine itself as a Windows program at a lower layer before even passing on the messages to the application. It checks what's the content. Then you have this routers, which also run some kind of network intrusion detection system. So for all incoming packets, that's already it. And there's probably somewhere some IDS management a station where all the logs are brought together and you can evaluate it. So collection point for data of the sensors, evaluation of data from several sensors. So this is for the case that, let's say, each individual line has acceptable request rate, let's say. But if you see that on different lines and the different different positions in the network, there's some orchestrated activity going on. This can be identified by the intrusion detection system management station, because it not just observes the traffic at one host or at one line, but is able to correlate all the activities on the various lines. Yeah, sometimes there's also obviously a database connected. But I mean, yeah. So this is typically so all higher activities must be put in some kind of external host that is more capable than a router. A router might be able to process the pattern seeking on the traffic, but it also has to be very fast, so it just can tell either there's no pattern matched, or there has been a pattern matching active. So the router would then send out the log to the management station. Okay, so lots of sensors are involved. Where should it be placed? Yeah, different placement might make sense. So first of all, if this is the internet and this is your first router, then it might also make sense to place it outside your first router in order to be able to observe all ongoing potential attacks in the outside world. Then there's the router with some kind of firewall, probably. And if you put some kind of intrusion detection system behind that, then you can see what your firewall filtered out. So you can compare the traffic before and the traffic after. Then you might have some demilitarized zone where you have also some servers. Let's say here you have some servers, web server. I don't know what else, email. That should be accessible from the outside world. There you could of course also have some kind of IDS included to see what traffic is going to the web server or coming from the web server or to your email. And then you have some internal further router with your internal network. So you can place these kind of intrusion detection systems basically at various points in the network which have dedicated roles. So outside, basically, then within the demilitarized network, within the private network, and also on, if here's some file server, also at critical hosts. But if you want to, you could also place an intrusion detection system at every host if you are able to. That's also one option, so that you can really observe any kind of traffic and have everywhere your eyes to detect potentially malicious traffic. So, and just as an example, let me just does it make sense to okay. So, and the problem is, or somehow the challenge, and where companies also come into play, is that you cannot apply too generic rules. So you have to a little bit adapt them to your needs. So you have to see what is applicable in your case and what is not applicable in your case. So let's say if some of the rules would be very critical about files exchange or some I don't know. So if you have some non-typical network activity in your network, then but because it's planned, because it's part of your business model, then you would get potentially lots of false alarms because it warns you about activities in your network, which is something that you anyway accept. So you have to balance the rule sets that you apply based on to get not too many false alarms. And yeah, acceptable resource consumption, that's always the question, whether on the long term there are sufficient resources to still operate it reasonably. Maybe one element, because where do you see the impact of such intrusion detection systems? So at my network at home, I have roughly 100 clients in the network, and for example, if I activate intrusion detection, then the bandwidth it drops from 1 gigabit per second to 100 megabytes per second. So it's a trade-off that you can consider. Do you really want to check every packet between your main machine and network attached storage for backups in order to potentially identify vulnerabilities, if at the same time the bandwidth drops to 10%. So it needs to be balanced. Okay, so if you do not balance it correctly and you do not apply the right rules, then you get lots of alerts in your mailbox. Your network traffic is delayed anyway, so again it drops from 1, at least at my setup, it drops from 1 gigabit per second to 100 mbit per second. It's also quite challenging to find out why this happened, but so this is somehow in the description. Or if you make it too loose, then some of the issues are not detected and you miss some of the potential attacks. So yeah, it needs some experience. As always said, there's some ongoing research. I mean, this is probably not the newest one. Now it's more AI related, that somehow it's auto-tuned, that you have some kind of AI supported rule setting so that it tries to balance the number of alerts to a specific grade. Let's say that you want only 10 messages a day, and it should tune itself that in a normal state without attacks it's doesn't reach higher numbers. So now in IT security and network related security, it's really I'm also now that 40%, 50% is about AI supported detection of vulnerabilities. It's a very hot topic. So actually, so lots of activities are now on AI supported vulnerability detection. So let's see how the regular historic static state-of-the-art activities are. So one of the network intrusion detection tools is Snort, and there should be some. Snort has a very nice logo with a pig and a big nose, so that actually looks through your data and detects malicious activities. You can also run it, so this is some open source tool. So what it does is very similar to Wireshark. It just tunes in and observes your traffic as Wireshark does and runs some rules on that. Rules, very similar to what the firewalls did, is just a pattern matching, but in contrast to firewalls, which let's say the regular ones on network layer, which look at IP address, port and TCP or UDP, it looks now into the whole message, so it's looked at. It can also be combined with IP tables so that it can stop packets, so that's an intrusion prevention system as well. It can also modify the contents of packets, but let's have a look at the detection at first. So it's simple to, we will have a quick look at how to set it up. So what it does is, so basically it looks at traffic passing this machine, and you can specify, I don't know what's the home network, because there's some distinction between external network and home network, and it logs everything that it observes, and you have to give that's the important file, the important element, to give a rule set that it should match the traffic with. Very similar to Wireshark, it just passes, it reads the traffic that is passing the machine, and compares it to this list of rules. How's the rule set up? No. Okay, let's see with the backup solution. So, how do the rules look like? So, the core idea is that every packet is checked. And for every individual packet, the rules are applied at. What is the packet consisting of? So it has a header and it has the payload. And in contrast to the regular firewall, not just the header is checked, but especially the payload. And if one of the rules match, then the action corresponding to it is performed. Yeah, and then the package is written to a log file. So what can you do? So either an alert can be an output to the console, pass to socket for further processing, write an email, trigger some activity. So there's some kind of potential reactions. But I mean, how it is implemented, what you trigger as an action is up to the configuration. It depends on what makes sense in your context. So you could, yeah. So how is it, for example, specified? So it depends. So let's say here the activity should be at the end, is at the begin. What should happen if the follow-up pattern matches? So if the packet is TCP packet, it comes from any source and is sent to the incoming network, to a specific port 111, and the content in the payload has this bit pattern. So 000186A5. This bit pattern is considered malicious. This is considered, so this is the message for the alert that mount so something is tried to be accessed, to mount some specific file system from remote. It has some identifier, some revision that's more for internal purposes, so if there are updates on the rules. But the main element is you specify what reaction. Then you have from which source, destination to which source, pattern, and then some info to give with the reaction if you rise an alert. Let's have a look at the real file for. So this is a real file from Snort. These are Snort community rules. So for example, if there should be an alert, if there's a TCP message from the home network, this IP and this port, to some external network, any port, and the content is this. Then, and the flow is to the client. It's an established connection. This message should be associated to the alert. I'm not sure what depth 16 means, but this is basically the pattern that you are looking for. Or if the content is this, if you find this a string pattern in the payload, then, and it's coming from outside to internally, then a message alert should be raised, and the message should be malware, backdoor, QA worm, client login access. There's some further information about what to present. So it's a rule set coming from the community, so it's not from the company behind Snort. Doesn't really make a difference on the pattern. There are some kind of classifications, mischievous activity. It has some kind of numbering. It has some revision number. And it's basically the local version of this rule. And you see we have quite a lot of rules. So here we have 4022 rules. What else do we have? If it's so it should be an alert raised. If it's an SSL protocol, so it's encrypted, it contains this bit pattern. I'm not really sure what. Obviously you can make it more and more complex, but is it or connected? So it's this content or that content or this, but within 4 distance to, if in close to this bit pattern, there's also some, I don't know. So, but you see, maybe to take a more simple rule, somewhere in the middle. This one, it's TCP message from outside, from any kind of port to an HTTP server, to HTTP ports. It's message to the server, to the HTTP server. It's an established connection. And this is the content that should be looked for. The case, so where that's big or small letters should not be considered. It's within the rule set of the community. It's associated to the service HTTP, some kind of references to other services, class types. But actually, this is the only element that you look for. But it should be TCP. It should be, the direction is also set. So it's very, as you see, you can have a lot of rules. I don't know, you have this kind of DG, DD, Y, CGI exe that somebody wants to call, or another exe files, other exe files. Let's say, do we have other kind of patterns? If somebody wants to access bash history at the server, if you have this kind of string, I don't know, somebody wants to get some application. So you see that these are very generic and simple to write rules. And obviously you can write your own rules by this way and look for potential activities that you are interested in. Okay, I'll try again. No, PowerPoint doesn't want to. Okay, so let's okay, so far with the network intrusion detection systems and what they can do and how they operate, and obviously by this you get some kind of continuous feedback on what generic and well-known attacks are ongoing in your network. It's quite useful, doesn't harm, doesn't cost too much. I mean, the processing of the 4,000 rules, or might also have more, takes time. So therefore your bandwidth is reduced. Yeah, but it's a nice, easy to apply approach. Okay, coming to the last point in this list that we had. Let's say we have somewhere in the network some home office worker that wants to be associated to, I don't know, to network branch A. So, I mean, here is the malicious internet in the middle, and here are some services that also so all employees want to use. So here's the file server, here's the printer. Think of any kind of service that is to be used by the employees. And we have typically two kind of cases. So on the one side, let's say this is the Bingen branch, maybe just more specific. So this is the Bingen, this is some site, some office in Bingen. Then you have some office in, I don't know, Mainz, and you have some office in, I don't know, Almaty. Okay, so, and now these are all belong to one company. So one of the use cases that you have is that the home office worker, of course, with changing IP addresses. So sometimes he or she is sitting in the train, has some IP address. Sometimes they're at home. Sometimes they're in some cafe, and they want to be part of this network so that they can access the file server, the printer, or if this would be TH Bingen, we have also some internal services such as, I'm not sure, the intranet or some configuration systems for internal network labs or so that you want to be able to access as if you would be locally present. Because as we have seen, typically you have this setup where the companies have a setup. Did we have it here? No. Yes, yeah. Let's take it this way. So because if we have some services here, the mail server, for example, that should be accessible from the outside world. But if you have a file server here, that should be not accessible to the outside world. Yeah, so nobody from the internet should be able to access it, except if you have here some home office worker, then this person should be able to access the file server internally. And the file server cannot distinguish between who's now a home office worker and who's an attacker. So you don't know the IP address up front to configure your firewall, so you need some other kind of mechanism to allow that all traffic of this home office worker is somehow redirected here to the internal network, and all traffic, even let's say there's some kind of broadcast for broadcast in LAN. So for in the local area network to find a printer. So if somebody starts some kind of local broadcast, it should act as if it would be in the same local network in order to find the services that are offered. And that, of course, through the internet is not really possible. It's not supported. It could be, of course, supported, but it's so unsecure, so you need some other means. So you somehow want to dynamically attach external devices, external hosts, as if they would be in the network themselves. And the other use case is that you want to have these sites also connected in a way that any kind of broadcast they have, any kind of message they send, should also reach the other sites. So for example, if this host here in Mainz wants to look for available printers, and then it should also find the printer in Bingen and in Almaty or so. So it should be some kind of virtual co-presence, although they are distributed. What options do we have? So option number one, to lay lines, so really to have some real connections. Sometimes this is done for very large databases, data centers, for security reasons, but obviously this is very expensive. You have to dig holes and lay physical lines, and this is not so easy to accomplish. Also, it doesn't scale, because here you would have, let's say, your regular connection to the internet where you pay money for, and then you have individual lines for all of the other network sites, so it doesn't really scale. So if you want to connect to 500 sites, then you would have to physically create this kind of strange topology and have additional networking edges reaching out. That's not feasible. Okay, obvious number one. So what you could do is let's say, can we use the already existing approaches that we have to use the available internet connection we already have? So could we configure our firewalls to allow the packets from IP ranges of the other sites to enter our system? So let's say the IP ranges here are known. This is IP range A, IP range B, IP range C, and you configure in your firewall to allow traffic from A passing to C and from B passing to C. So what kind of issues do you see with that kind of approach? Is it reasonable? Is it good? So let's make an example. So let's say this is TH Bingen's IP address here, and then we have 128.25. So all basically from 128 to 255, this IP address would be considered as IP range of A, and then we write here rule except source from element of A.
So it allows separating when one network is infected and the other network.
So you said if one host or one network would be affected, it would spread to the other networks. That's right, but that's also the case. I mean, we want to mimic the feature that they should act as if they would be co-located technically. So if they would be co-located and one part of the network would be affected, infected, then also the other parts would be affected. So they would get some impact on their behavior. So that might not be a bug, it might be a feature. So, because that means that there's security is at that point a second consideration. So the first element is that, so what kind of characteristics do you have if you are in the same network? So first of all, you have this MAC to IP resolution, meaning that ARP requests are going through, so that you have the feeling as you have a very big one-hop neighborhood, so that you don't have to pass routers. Especially that allows you to find services in your surrounding, to connect to them directly, and you can very easily configure services to use other services, and you just assume it works and the traffic will go through. And this kind of behavior we want, so especially service discovery, and service access. Off to potentially unsecure. Unsecured machines. So the idea is, yes, we have here some firewall at the router side, but behind it's all considered, they are all checked, the traffic is checked, and behind that we can just communicate simply between the devices, between the hosts. And now we want to put part A as accessible from C as B is accessible from C, so as if there would be no intent in between. So if you put this kind of rules in the firewall, well, the first element would be, yes, the traffic from A would be able to pass to C, let's say, but everybody claiming to be from A would also gain access to C. So it's true, they do not get the response. So let's say here's Trudy, and Trudy learned, oh, there's a firewall exception for traffic coming from A. So what she does is she spoofs her IP address. That means she claims that she's from A and sends messages to C. The answer will go back from C to A, that's right. So the answer will go this way. But the question will be whether Trudy might send out some malicious messages that cause some harm. One of the simplest attacks that Trudy could do is, again, a distributed denial of service or some regular denial of service, just sending requests to the internal devices under C, and at the firewall of C, it's not identified that this is coming from somewhere else, so they pass through, and this request might already consume some resources at C, so that some services are not useful. So basically, due to the spoofing attack, we don't have a confirmation of whether the messages are really coming from A, or whether just somebody claims that they are A. So it's not sufficient to apply firewalls. Okay, but what could be created is a so-called tunnel, or some kind of virtual lines over the internet. So what it basically does is that some kind of virtual network card is created in routers and branch offices A and B. So the idea is, this is the this is the final router in A, the red machine. Yeah, so you see the red machine there, and what we can do. Sorry. So if all of these regular hosts connected to this red machine, the machine now acts as a router. So what does it have? It connects it to the ISP. Yeah, here's the regular internet service provider. And the router typically, what it also have, as we had in the overview on regular networking, it has a forwarding table. So it decides through which of its ports does it forward messages it receives. Forwarding table. Typically, in a regular household or company network, you just have one single link that you can forward your messages to, that of the internet service provider. But in this case, there's a second network card, a second link entered. So this one, let's say, one option is to send the messages to the internet service provider. And the second option is to send it to a virtual line or virtual port or whatever, something virtual, which processes somehow the data, and then it sends it to the ISP. So, packets are sent over this virtual line interface do not end up on the transmission medium, but in special software. This software encrypts the packets and sends the resulting data over the internet to its counterpart in the other branch. So what happens? Let's say all of the messages. So if this is endpoint of network A, so everything that is directed to B and C is sent to this forwarding line. So not here, but here. So B and C is sent to the virtual line, and everything else is going to the regular ISP. So, and what does it do? It takes the message, and I think I have it on the next slide. So, yes. So what it does is it takes the messages that are meant for B and C, it encrypts them, it adds some authentication information to show that it's really from network A, from the VPN, virtual private network, endpoint of network A. So it adds all the nice elements. So it adds confidentiality. That means encrypt for B or C. It adds integrity plus authentication, so that it verifies that this is really the message that came from A. So, and on the other side, and who's the new destination? So previously, let's say we had here a packet with destination IP in B. So that might be destination was the printer. So the destination in B was the printer, and now the VPN endpoint in network A modified the destination, encrypted that packet, and basically wrote destination now is the VPN endpoint of B. So it changed the recipient from the printer to the only accessible access host for this VPN, and that's this endpoint of the other network. So, and now this packet, so this green one, with the encrypted content, with the new header, with the new, so it has been packaged, is now sent to the endpoint of B using the regular previous ISP. So now the message comes in. So this, we are now at the network of B, and now here we get the encrypted and the package. There's nothing visible about. So if Trudy looks at this packet, looks at the packet, she doesn't see who has been addressed within B. She just see that the VPN endpoint of B is addressed. She cannot read the content because it's encrypted. She cannot modify the content because there's authentication information in it and integrity is provided. And now the VPN endpoint receives the packet. It verifies the authenticity. It verifies the integrity. It decrypts the message, and it unfolds, unpackages basically the for whom the package is meant. So in this case, the printer, and then it releases it within the local network of B. So by this, any kind of, so if this is A and this is B as big networks with many hosts, so what they do is basically once, if any of these services want to communicate to somewhere else in B, they send their message to their local router. At the local router, there's the VPN endpoint. The VPN endpoint has a kind of ongoing traffic with the other VPN endpoint, and then here it is released again. And this that you can apply for any kind of messages, ARP requests. It can be on ICMP messages. It really, yeah, especially for ICMP messages, that's an interesting element. We had, for example, traceroute. I think did we have traceroute? Yes. So how many hops it takes you to go to your destination. So if you have here hop number, let's zoom in. Is it working? So if you have here hop number 1, let's say there's another one, hop number 2, this is hop number 3, then there are many hops in between, but the next time it is processed, here's hop number 4, hop number 5, and I don't know, hop number 6. So for the ICMP message that is forwarded through this tunnel, it is not active, so it's just a package that is transferred from the VPN endpoint A and to the VPN endpoint B, and then re-released in the local network and continues and is processed later on. So it doesn't see any tunnel in between. So it's basically really like a tunnel. It's where the messages are shipped from A to B and from B to A, back and forth, and to both participants in the network, both to A as well as for those in B. They do not distinguish, they cannot identify whether there's a tunnel in between or not. For them, it's just regular, as if the network would be connected over these routers. So they don't see any in between. Especially, let's say, if you would, let's say, use a traceroute as we had that example, and you just check which IP addresses are active in your local network, then your scan traffic will also pass on through the tunnel, and it's re-released at the new network and then continues to scan further on, so you don't see that the tunnel has been involved. Also, if you search for a printer, I don't know, then maybe some kind of IP ranges are scanned, and for the scanning, some lower layer messages are used that also typically would not be able to pass through the internet, but here it's really everything that is destined to a recipient in B is just passed on through that tunnel and re-released then at that site as well. So this connection is called tunnel, and the concept is called virtual private network, and you can use it basically for two purposes. Purpose number 1, do I have here the example? You see. Let's have a example here again. So let's say you have here the internal network with this IP addresses 1200. So it's basically have the subnet mask of 16. That means the first 16 bits mark the ID of the subnet, and the rest, so basically this 0 and this 0, could be anything else. Then we have here a local IP address for the firewall A on this side, and a public IP address for the firewall on the internet facing side. The same for the firewall B, and the same for the internal address scheme for the second private network. Here we have the IP addresses of 1.3 point whatever, so 00. The first 16 bits are fixed, the rest can be modified. So now, basically, if the VPN now is implemented in a way that if the destination is 1.3 point something, then this second device should be used to send out the message. And the same here, so if the destination is for 1.2 point star star, then it should be sent to this device as an outgoing port. So and now it is quite simple to configure our firewalls. So basically we can specify that we permit. So the firewalls are now simple to achieve. So if previously we would have to somehow make sure that traffic is not coming from this connection point to the internal network, and we would have to somehow filter for the IP addresses used, which are not really routable in the internet. Now we can clearly define, so if the traffic is coming, so in a case, from this network interface, and it has as the destination this IP address range, then it's allowed to pass. So we can really make the decision based on the interface that the messages come from. So everything from the tunnel is accepted, and obviously the virtual private network algorithm, so the software makes sure that only traffic really coming from the other side through authentication, integrity, confidentiality is passed through to the firewall, and it's previously verified. So everything on a side that's coming from this interface, we can basically allow to pass internally, and if it comes from this interface, then we should be very suspicious and consider it as potentially malicious. So now it's really easy to be compatible with the firewall rules and to achieve what we wanted. Maybe another point, because we were also talking about the potential of the home office worker. So now let's say we have here another home office worker. He has also some VPN, and I don't know, his internal network is very small, so internal network is just one host with a specific IP address. So what he can now do is to start his VPN and assign its VPN to connect to, I don't know, to be here. So they should establish a connection. What needs to be established? So there needs to be first an authentication. So the home office worker needs to verify that he is really the person that has the access right. Then there's some key exchange, and based on this key exchange, there are some further keys derived for integrity of communication, and especially for the confidentiality for encryption. So it doesn't make any sense, any difference anymore, whether it's a big network that is connected to another big network, or whether it's a single device, a single host connected to another network. They are both connected in the same way. So any kind of broadcast that is happening here in A, somebody's looking for an ARP request, so basically wants to find out for a given IP address who has a specific MAC address that's typically broadcasted. This broadcast would pass from the network A to the network B and to the home office worker as if they would be in the same network. Okay. So we will have, especially then in later, in the next lecture, I think, have a look at how this key exchange is taking place. So what kind of information you need to exchange to gain that information, that you verify yourself, and that you get the right key. Yeah, maybe to introduce, yeah, okay. First we will learn that, and then we see how this can be also done. Okay, so how is this technically implemented? They are in principle very similar. So what would you do? What needs to be achieved? Yeah, as I said, what you need first is to have VPN software running associated to the routers to be able to have this virtual network card that actually does a lot of processing in order to encrypt the messages and to send it to a specified destination. So you need first the software, you need some kind of means of authentication, you need some key exchange, and once you have exchanged the keys, then you have typically some kind of integrity using hashes as well as encryption for confidentiality. And of course there are some various differences. I mean, how authentication is done, how secure, or what kind of keys are exchanged, what protocols are used. But from the process, it's always the same. So first you have the software that allows you to have this virtual private card, a virtual network card, authentication, key exchange, and so on. Okay, let's have a look. Yes, okay. So what we can also have a look at what layer you provide this tunnel. So you can either have it at the layer 3. So basically it is this is so. So what you can have it is that either it acts. So the question is, you have this network, you have this VPN endpoint, and you have here another network, A and B. So the question is it based on IP addresses? How it is decided what messages are passed through? Yeah, it's like its own IP segment that you really make the decision to route over this tunnel based on the IP address. Yeah, decision made based on IP address, or whether you make it based, or you want to create it as if it would be in the same one-hop neighborhood. Yeah, so you could also send Ethernet frames. What is the difference? Oh, sorry for this text IT. This is some LaTeX fragment. Okay, so what does it mean? So that means, let's say if this is A, and you want to communicate based on, and we have here the IP address 10.2.0.0, and here we have 10.3.0.0. Then if it's based on layer 3, then basically you only send the messages that are directly addressed to 1.3.0.0 to the other network VPN endpoint. So you can make it, that means that what messages do you miss? Especially you miss messages such as ARP requests, where you typically just in Ethernet broadcast to find out what IP address is associated to which MAC address. Maybe some ICMP messages are, so typically all the broadcasting, so no broadcasting. This is some main difference. Because if you would have it based on Ethernet frames, then it would be like between two switches or bridges. So it's with Ethernet L2, you have also broadcasting. So typically that, I mean, it depends what kind of purpose you want to fulfill. So if it's based on Ethernet frames, also broadcasting supported, then you really act as if they would be even in the same communication space, and every every host from here can reach every host from here in one single networking hop. So they are as if they would be connected over a switch. If you use layer 3 tunneling, then you dedicatedly have to address that external node, and you are not in the same one-hop neighborhood, but in the same two-hop neighborhood. So you need to first go to the router, and then from the router to the destination node. Yeah, it depends what you want, how strongly you want to connect them. Especially you in layer 2, all networks are virtually the same that you connect. And in layer 3 networks, you can have distinctions based on IP addresses and to exclude some of the hosts, but it depends on what you need. Just wanted to point that out. So, so the term layer 2 or layer 3 tunnel really just tells what's inside of the tunnel packets. That means whether you put layer 2 Ethernet frames in it, and that is what you send, or whether you have as a recipient basically router 1 or this virtual private network router 1, and you lose the information of where it came from and you just forward it to the other router. It depends. It depends on what purpose you want it for. So, another question. If you set up a tunnel between two sites, A and B, over what kind of connection do you send the encrypted packets from A to B? Or another kind words, what kind of wrapper do you put your encrypted packets in? What we had shown here is, yes, you have some encryption, so you have some kind of header here. You have some kind of encryption information. But what kind of outer shell, what kind of packet type is that? So what would you put it in? Is there some limitation? Because now let's say we have here VPN endpoint of B. Yeah, and its purpose is to receive the messages with the header, and then basically to decrypt it, to verify authentication, and then to release into the own network what's the message. And here we have the VPN endpoint of A. And some of the packets are coming here along with the destination of B. And then they are packed with some new header. And here's the information that we had previously. What kind of in what kind of traffic do we, this is some kind of encapsulation, as you see. So we take an existing packet and put it into a new one. And this new packet could be of various type. It could be, for example, an HTTP message, which has a body type, which contains the package of what you want to send. It could be a newly formed packet type that's very new. You define it, and it has a clear header and content. But this is some application layer information. I mean, you can freely define how this packet looks like. So if you think of HTTP, what kind of, it doesn't really have a header. You just start with get index HTML follow HTTP 1.0. So you can really define how the message should look like. There are no real constraints. So what you can do is to really put it in any kind of different packets as you want. So you could hide it in HTTP traffic, and the HTTP server is in fact just a VPN endpoint that takes the HTTP packet, drops all the unnecessary parts, and decrypts the content and so on. But it could be also different kind of packets that you just make up. Okay, so one of the examples where you could put it in is iodine. Is it right? Is it right? Yes. So for example, so what it for example does is lets you tunnel IP version 4 data through DNS servers. So what you for example could do is, it sounds a little bit strange, why to put IP version 4 data in DNS traffic. But what you could for example do, okay. Okay, so what you for example could do is to set up a DNS server that listens to port 35, but in fact it's a VPN endpoint. And if you are somewhere with your machine and you want to send some traffic, but you want it to be released here, so basically here should be your traffic, and here is your traffic. What this iodine does, as an example, is that it takes your traffic, it adds all the right header information. We will have a look how authentication and so is done. But it sends it to your DNS server. Why would that make sense? So for example, just to put it in DNS traffic, because this is now a DNS request. So the format of the file would be also DNS compatible. So it really looks like a DNS traffic. There's a request in the DNS. Let's have a look at DNS messages. Maybe there's a recapitulation. DNS request. I don't know what kind of. Good. That's maybe not the best one. DNS request. Where do we have one? I don't know. Just, do we have an example here? No. It's not too complicated. It just tells, okay, I have this URL and I'm looking for the corresponding IP address. And this URL could be very long. So you could put in some information that is somehow containing the encrypted data. I see some other example. No, I'm not. I don't know. It's still very simple. As a domain name service just has this very simple setup. You send an URL and you want to get the corresponding IP address. And to whom do you send it? To the DNS server you specified, and in this case the DNS server is associated to you. And what you could do is to hide traffic in DNS URL. Any idea why this might have some reason? Why to use DNS? It's not very convenient. Have you any time used the Wi-Fi portal? No Wi-Fi portal? Where, I don't know, enter your credentials to connect at a hotel, at the airport. Okay, and typically this Wi-Fi portal is accessible through an URL. There's written hotels.wifi-portal.com, so I don't know, hotel name / Wi-Fi. But in order to, IC portal, I don't know, so it's maybe this IP, this URL that is used, and here you can enable exactly, it's the case. You connect to the Wi-Fi, and then you visit this this URL. But how do you know what the IP address of this URL is? You need to perform a DNS lookup. But which DNS server do you ask? The one configured in your local machine. So in Wi-Fi portals, typically DNS access is permitted. So you can send messages to a DNS server of your choice to look up the IP address for this portal address. And how many messages can you send to this DNS server of your choice? As much as you want. So you could, for example, set up a VPN using your modified DNS server at home or somewhere, and send as much traffic to that DNS portal without accessing the portal that has been recommended to you. If you want to use the Wi-Fi, visit the portal and pay money, I don't know. You just send out your traffic that you have to your DNS server, because traffic to your DNS servers is permitted. So this is one way to hide messages in basically in publicly visible communication. It's encrypted. The portal owner permitted to use DNS to allow DNS traffic to any kind of server, and this would be one potential way to set up a VPN tunnel communicating with your public DNS server, which is internally processing your encrypted data and sends, of course, replies back. And here you have some kind of communication ongoing, although you didn't accept anywhere some kind of portal conditions. One example. A more general question is, should it be, so DNS is using UDP. UDP. So should you use UDP because it's just typically one question and one answer, you don't need to establish the connection. But of course we could also have TCP. So what should we use? Should we use UDP as a basis for our traffic, or should we use TCP? Keep in mind that once our traffic, whatever it uses, maybe we use HTTP to look up data, it uses TCP, then this is encapsulated and this is sent out through VPN. The question is UDP or TCP, and then it's passing on through the real network, and then the message is unpacked again, and TCP is applied, and HTTP. So should we have, basically the question is, if we are using TCP with TCP, what's the effect? Or if we are using UDP with UDP or UDP with TCP, what is the effect of the combinations UDP in the encrypted data using some underlying UDP? What if we use TCP and UDP? So this is the VPN, and this is the application that is encrypted. What happens if we have UDP over TCP? And what happens if we have TCP over TCP? Any idea what kind of combinations is good or bad? So we have to decide, do we want to go for VPN traffic over UDP, or should we go over VPN traffic over TCP? What should we select? So what is TCP in contrast to UDP doing? So what are the benefits of TCP over UDP, let's say? So this is my hope is always that from previous Kone, so the communication networks, there's some kind of lingering memory. Okay, so basically UDP is very simple. It doesn't do anything. It just sends the message, and if the message is lost, then it's lost. If you send too quickly, then you send too quickly. Messages get lost, no problem. And in TCP also in the VPN part, what it does is if messages get lost, they are resent. If the transmission speed from the sender is too high for the recipient, it communicates back and the transmission is reduced. And the question is, what happens if we combine two UDP UDP over UDP? Doesn't matter on which element, which side the messages get lost, they anyway get lost. The question is more, what happens if you apply TCP on TCP, whether this is an issue or not. So what do we have? TCP has all its reliability mechanisms and overload control. The UDP is very simple. But if we have TCP over TCP, just consider that some message is lost, then this layer will reduce the transmission speed, and this layer will also reduce the transmission speed. So if you have some problem, then on two sides you are reacting to it. And let's say if this reacts to it and limits the speed by which the messages are passed through, this higher layer considers it as limited network power and also reduces the transmission speed. So basically you have two control loops trying to optimize the throughput that are counteracting each own actions. So combining TCP with TCP is not very good, so you should use UDP as one control loop is sufficient. Okay, so next time we will continue with that and also have a look at DDoS, denial of service attacks. Final element, please visit the Industrie now on Wednesday, and otherwise thank you for